Beyond Relativity by N. Stories. Part 1. The Foundations of Special Relativity. Chapter 1. Why Space and Time Aren't What We Think. For thousands of years, people believed that space and time were as reliable as the rising sun. The world seemed predictable. A stone thrown through the air followed a familiar path. A horse pulling a cart moved at a speed anyone could estimate. A clock ticked steadily on a wall, measuring the passing seconds in exactly the same way for everyone nearby. These experiences shaped humanity's understanding of reality. The great English scientist Isaac Newton built one of the most successful scientific systems in history using these everyday observations. According to Newton, space was like an enormous stage upon which every event in the universe unfolded. It never changed. It was fixed, empty, and absolute. Time behaved in much the same way. Whether someone stood on Earth, sailed across the ocean, or imagined traveling among the stars, one universal clock measured time equally for everyone. For centuries this picture worked remarkably well. Engineers designed bridges, astronomers predicted planetary motion, and sailors crossed oceans using calculations based on Newton's laws. His ideas explained almost everything people could observe with the technology available at the time. Yet nature had been quietly hiding a secret. As scientists built more accurate instruments during the 19th century, they began discovering strange behavior that didn't fit comfortably within Newton's framework. The greatest mystery involved something so familiar that most people rarely stop to think about it: light. Unlike a moving carriage or a flying arrow, light behaved in extraordinary ways. It traveled incredibly fast, around 300 million meters every second. More surprisingly, every careful experiment suggested that this speed remained constant regardless of how the observer was moving. Imagine standing beside a railway line. A train passes at 100 kilometers per hour. If another train travels in the same direction at 120 kilometers per hour, someone on the faster train sees the slower train moving away at only 20 kilometers per hour. This seems perfectly natural because speeds simply add and subtract. Now replace the trains with a beam of light. Common sense suggests that if you could somehow chase a beam of light at half its speed, you would measure it traveling only half as fast. But nature refuses to cooperate. No matter how quickly you move, every measurement shows the light racing away at exactly the same speed. At first glance, this sounds impossible. How can two observers moving at different speeds both measure exactly the same speed for the same beam of light? This question puzzled many of the brightest scientific minds of the era. Physicists proposed the existence of an invisible substance called the luminiferous ether. According to this idea, light traveled through an unseen medium filling the universe, much as sound travels through air or waves travel through water. Earth, moving around the sun, should have been traveling through this ether, creating an ether wind. If the ether existed, careful experiments should have detected Earth's motion through it. One of the most famous scientific experiments ever performed attempted exactly that. In 1887, Albert A. Michelson and Edward W. Morley designed an incredibly sensitive instrument capable of detecting tiny differences in the speed of light. Their expectation was straightforward. As Earth moved through the ether, light traveling in one direction should take a slightly different amount of time than light traveling at right angles. The experiment was elegant. A beam of light was split into two separate paths before being reflected back together. If one beam traveled slightly faster than the other, the returning light waves would interfere with each other, creating measurable changes. The result shocked everyone. Nothing happened. No matter when the experiment was performed or which direction the apparatus faced, the speed of light appeared identical. Scientists repeated the experiment many times with increasing precision. The answer remained stubbornly unchanged. The ether could not be found. This presented an enormous problem. If light required no medium through which to travel, and if its speed remained constant for every observer, then something much deeper about the universe had to change. Many scientists attempted to rescue the old ideas by introducing increasingly complicated explanations. Some suggested objects physically shrank as they moved through the ether. Others proposed that time itself somehow adjusted during motion. These explanations solved individual problems but lacked a convincing physical reason. Then, in 1905, a young patent examiner working in Switzerland approached the problem differently. Albert Einstein asked a simple but revolutionary question. What if the experiments were correct? Instead of trying to explain away the strange behavior of light, perhaps our assumptions about space and time were wrong. Rather than modifying light to fit existing physics, he proposed modifying our understanding of reality itself. Einstein began with two deceptively simple principles. First, the laws of physics should be identical for every observer moving at a constant speed. Whether sitting quietly in a room, traveling smoothly aboard a train, or drifting through space in a spacecraft, the basic rules of nature never change. Second, the speed of light in a vacuum is always the same for every observer, regardless of how fast the source or observer moves. These statements appear harmless. Yet together they overturn centuries of intuition. If everyone measures the same speed of light, then distances and time intervals cannot be absolute. Instead, they must adjust depending on the observer's motion. In everyday life, these effects are so tiny that we never notice them. A car traveling along a motorway moves far too slowly compared with light for measurable changes to occur. Even the fastest commercial aircraft travel at only a tiny fraction of light speed. Our daily experiences therefore reinforce Newton's picture because, at ordinary speeds, it is an excellent approximation. However, as speeds approach that of light, the universe begins behaving in ways that seem almost magical. Clocks run more slowly. Distances shrink. Events that appear simultaneous to one observer may occur at different times for another. Mass and energy become deeply connected. None of these effects are illusions. They are genuine features of reality confirmed by countless experiments over the past century. Perhaps the most surprising lesson is that common sense is not always a reliable guide to nature. Human intuition evolved to help us survive in forests, fields, and villages, not to understand particles traveling near the speed of light or the structure of the cosmos. Science repeatedly teaches us humility. Every generation believes it has discovered the final truth, only to find that nature is richer, stranger, and more beautiful than anyone imagined. Special relativity represents one of humanity's greatest examples of this lesson. It did not discard Newton's achievements. Instead, it revealed that Newton's laws describe a special case of a much larger and more elegant picture. At low speeds, classical mechanics remains extraordinarily accurate. At extreme speeds, however, Einstein's theory takes over, revealing a universe where space and time are woven together into a single fabric known as spacetime. Understanding this idea requires us to let go of familiar assumptions and embrace a new way of thinking. The reward is profound. Concepts that once seemed impossible begin fitting together into a coherent description of reality, one that explains everything from particle accelerators and GPS satellites to the life cycles of stars. Chapter 2: The universe has a speed limit. When faster isn't always possible. Imagine standing on a beach watching the waves roll toward the shore. Some are small ripples, others are powerful breakers, but they all move through the water at speeds determined by the conditions around them. Now imagine shining a flashlight across the beach at night. The beam of light reaches distant objects almost instantly, racing away far faster than any wave or anything you've ever experienced in everyday life. This simple comparison highlights one of the most remarkable discoveries in science: the universe appears to have a built-in speed limit. That limit is the speed of light in a vacuum, approximately 299,792,458 meters per second, or just under 300,000 kilometers every second. To appreciate how astonishingly fast this is, consider that light could travel around the Earth's equator more than 7 times in a single second. It reaches the Moon in about 1.3 seconds and travels from the Sun to Earth in just over 8 minutes. For centuries, people assumed that speed simply added together. If a person walked forward inside a moving ship, their speed relative to the shore would be the ship's speed plus their walking speed. This works perfectly well for almost everything we experience in daily life. But nature has a surprise waiting when we deal with light. A different kind of speed. Let's imagine the year is 2150. Humanity has built a spacecraft capable of traveling at half the speed of light. Inside the spacecraft, an astronaut switches on a powerful laser and points it toward the front window. What would an observer on Earth measure? Our everyday intuition suggests a simple answer. If the spacecraft is already moving at half the speed of light, then surely the laser beam must travel at 1.5 times the speed of light relative to Earth. Yet every experiment ever performed tells us that this is not what happens. The observer on Earth measures the laser beam traveling at exactly the speed of light. A family car traveling at 100 km per hour is moving at less than 1/10,000,000th of the speed of light. Even the fastest passenger aircraft reach only a tiny fraction of light speed. At such ordinary speeds, the effects predicted by relativity are so incredibly small that even the most accurate wristwatch could never detect them. Newton's laws work brilliantly because they are an excellent approximation for slow-moving objects. It's much like using a flat map of your local town. The Earth is actually curved, but over short distances the curvature is too slight to notice. Relativity doesn't replace Newton's description of motion, it expands it. Newton's rules remain useful wherever speeds are relatively low. Einstein's insights become essential only when motion approaches the universe's ultimate speed limit or when gravity becomes extremely strong. Science often works this way. New theories don't always erase older ones, they reveal the conditions under which those older ideas remain valid. A cosmic speed limit, not a technological one. When engineers build faster aircraft or more powerful rockets, they often overcome previous limits through innovation. Breaking the sound barrier once seemed impossible until new designs and better engines made it routine. The speed of light is fundamentally different. It is not an engineering challenge waiting to be solved. It is woven into the fabric of reality itself. Imagine playing a board game where no matter how skilled the players become, they can never move more than 6 spaces in a single turn because the rules simply don't allow it. The limit isn't due to weak players or poor equipment, it's part of the game's design. The universe appears to work in much the same way. No object carrying mass can be accelerated all the way to the speed of light because doing so would require more and more energy as its speed increases. As it gets closer to light speed, each additional increase in speed demands an ever larger amount of energy. Near the limit, the required energy grows so dramatically that it effectively becomes unreachable. This isn't a failure of technology, it's a consequence of how the universe is built. Information cannot outrun light. The speed limit applies to more than just rockets and spacecraft. It also governs how information travels. Suppose the sun were to disappear instantly, a purely imaginary scenario. You might expect Earth to drift away immediately because the sun's gravity had vanished. Surprisingly, that isn't what would happen. For about 8 minutes, Earth would continue orbiting as though nothing had changed. Only after those 8 minutes would both the last sunlight and the change in the sun's gravitational influence reach us. This tells us something profound. The universe has no system for sending information instantaneously across space. Every event takes time to influence another. In a sense, the cosmos is having a conversation with itself, but every message, whether carried by light, radio waves, or changes in gravity, travels at a finite speed. That simple rule preserves order in the universe. Causes come before effects, and distant events unfold according to a universal rhythm set by the speed of light. Chapter 2: The Universe Has a Speed Limit, continued. Testing nature's ultimate rule. One of the greatest strengths of science is that ideas must survive experiments. A beautiful theory is interesting, but until it matches reality, it remains only an idea. Throughout history, many scientific theories have seemed convincing at first, only to be abandoned when evidence showed they were incomplete. The idea of a universal speed limit faced the same challenge. If the speed of light really was constant for every observer, scientists needed to find proof. Fortunately, nature provided many opportunities. One of the most powerful testing grounds isn't found in the sky but beneath the Earth's surface, inside enormous machines known as particle accelerators. Imagine trying to understand how a watch works. Looking at it from the outside tells you very little. You need to examine the tiny gears inside. Physicists use particle accelerators for a similar reason. Instead of taking apart a watch, they investigate the smallest building blocks of matter. These machines use electric and magnetic fields to accelerate particles, such as electrons and protons, to incredible speeds. Some reach more than 99.9999% of the speed of light. If Newton's understanding of motion were the whole story, these particles should eventually exceed the speed of light as more and more energy is added. But they never do. Instead, something fascinating happens. Each burst of energy still affects the particle, but rather than increasing its speed by the same amount, the particle becomes increasingly difficult to accelerate. It's as though the universe resists every attempt to push it closer to the cosmic speed limit. Imagine trying to push a shopping trolley across an empty supermarket floor. At first, every shove makes it move much faster. Now imagine that, as the trolley gains speed, it somehow becomes harder and harder to push. Eventually, you could apply enormous effort and see only the tiniest increase in speed. That isn't how shopping trolleys behave, but it's remarkably similar to what happens with particles moving near the speed of light. The closer they get to that limit, the less additional speed they gain from each new input of energy. The universe seems to be saying, you may approach this limit, but you cannot cross it. A universe that protects cause and effect. Why would nature impose such a restriction? At first glance, the rule seems inconvenient. Wouldn't faster travel make the universe more efficient? To answer that question, we need to think about something even more fundamental than speed. We need to think about cause and effect. Suppose your friend sends you a text message saying they have arrived safely at home. Normally, the sequence is obvious. First they arrive. Then they send the message. Finally, you receive it. Now imagine information could travel infinitely fast, or even faster than light. Under certain circumstances, the order of events could become scrambled. Different observers might disagree about which event happened first. In some situations, a reply could appear to arrive before the original message had been sent. This would create a universe filled with paradoxes. Imagine receiving tomorrow's lottery numbers today. Imagine warning someone about an accident before it had happened. Imagine preventing an event that had already caused you to send the warning. These kinds of contradictions don't fit with the orderly universe we observe. By limiting the speed at which information can travel, nature preserves the relationship between causes and their consequences. Every event has time to unfold in a consistent order. It's one of the hidden ways relativity protects the logical structure of reality. The everyday world hides extraordinary truths. If someone told you that clocks slow down, distances shrink and time flows differently depending on motion, you might reasonably ask why no one notices these effects while driving to work. The answer is simple. Human life unfolds at incredibly slow speeds compared with light. Consider a snail crawling across a garden path. From the snail's point of view, its journey may seem significant. Yet compared with the speed of a racing car, its movement is almost negligible. Now compare a racing car with light. The difference is vastly greater. Even the fastest Formula One car is practically standing still compared with a beam of light. Because our everyday experiences occur so far below the universe's speed limit, relativity hides itself remarkably well. It's like looking at the ocean from an aeroplane. From high above, the surface appears perfectly smooth. Only when you descend closer do you notice the individual waves. Relativity is always present. We're simply moving too slowly to notice most of its effects. Relativity in your pocket. One of the most surprising facts about modern science is that many people use relativity every single day without realizing it. Consider your smartphone. Whenever you ask for directions, order food, track a parcel, or find the nearest petrol station, your phone communicates with satellites orbiting thousands of kilometers above Earth. This system is known as the Global Positioning System, or GPS. GPS works by measuring incredibly precise travel times for radio signals sent between satellites and receivers on the ground. Here's the remarkable part. The clocks aboard GPS satellites do not tick at exactly the same rate as clocks on Earth. Some of this difference comes from their high orbital speed. Another part comes from the weaker gravitational field experienced far above Earth's surface, a consequence we'll explore later when we discuss general relativity. Although these timing differences are tiny, measured in millionths or billionths of a second, they accumulate rapidly. If engineers ignored relativity, GPS errors would grow by several kilometers every day. Within a short time, navigation systems would become useless. The fact that your phone reliably guides you to the correct street is quiet evidence that Einstein's ideas describe the real universe. Relativity isn't confined to university lecture halls. It helps people find restaurants, airports, and hospitals every day. Light is the universe's messenger. Whenever astronomers study distant galaxies, they are really studying light. Light carries stories. Every beam arriving at Earth has traveled across space, preserving information about the object that emitted it. Some of the light-entering telescopes tonight began its journey before human civilization existed. Some started traveling long before dinosaurs walked the Earth. Some has been crossing the universe for billions of years. Looking through a telescope is therefore unlike looking through an ordinary window. It is more like opening a history book written in light. Because light has a finite speed, distance becomes another way of measuring time. A galaxy 1 million light-years away appears as it existed 1 million years ago. A galaxy 1 billion light-years away shows us conditions that existed long before our own solar system had fully formed. The speed limit of light allows astronomers to explore the past simply by looking deeper into space. In a remarkable twist, the farther we look into the universe, the farther back in time we see. The hidden thread connecting everything. By now, the idea of a universal speed limit may seem less like an inconvenience and more like a guiding principle. It shapes motion. It governs communication. It protects cause and effect. It allows us to measure the universe. It even lets astronomers peer into cosmic history. Yet one mystery still remains. If everyone measures the same speed of light, what exactly changes instead? We've hinted at the answer throughout this chapter. Space adjusts. Time adjusts. But how? Can two identical clocks genuinely disagree after following different journeys? Can one traveler really age more slowly than another? Could astronauts leave Earth, travel at extraordinary speeds, and return younger than the people they left behind? As unbelievable as these ideas sound, careful experiments have confirmed them again and again. The universe is not merely stranger than we once imagined, it is stranger in ways that can be measured, tested and understood. In the next chapter, we'll explore one of the most astonishing consequences of relativity: time itself is not fixed. We'll discover why motion changes the passage of time, how scientists have measured this effect with astonishing precision, and why every person's journey through the universe is accompanied by their own unique clock. Chapter 3: When Time Begins to Stretch. Section 1: The Clock You Never Notice. Have you ever looked at a clock during a long day at work and felt as though time had almost stopped? Then, on a weekend spent with friends, the hours seemed to vanish in what felt like minutes. We all know that sensation. Psychologically, our perception of time changes constantly. Physics, however, is interested in something very different. Imagine placing two identical clocks on a table. They are built from the same components, tested to the same precision, and started at exactly the same moment. If one remains in your living room while the other is carried on a journey around the world aboard a high-speed aircraft, what happens when they are reunited? Your intuition probably says they should still agree. After all, a second is a second, isn't it? For most of human history, that answer would have seemed obvious. Time was believed to flow like a perfectly steady river, carrying everyone along at exactly the same pace. Whether you were climbing a mountain, sailing across an ocean, or sitting quietly under a tree, every person shared the same invisible cosmic clock. But modern physics tells a far stranger story. Time is not a universal river. It is more like countless individual streams, each following its own path through the landscape of the universe. Usually, those streams run almost perfectly side by side, making them appear identical. Only when motion becomes extreme, or gravity becomes immense, do they begin to drift apart. What does a clock really measure? Before we can understand how time changes, we need to ask a surprisingly simple question. What is a clock? Most people picture a wristwatch, a grandfather clock, or perhaps the digital display on a mobile phone. Yet these are only different tools for measuring the same thing. At its heart, a clock is simply a device that counts regular events. A pendulum swings back and forth. A quartz crystal vibrates thousands of times every second. An atomic clock measures the natural oscillations of atoms with astonishing precision. The design changes, but the purpose remains the same: count repeated events. Now imagine something extraordinary. Suppose every process inside a moving clock slows down together. The pendulum swings more slowly. The crystal vibrates less frequently. Even the atoms themselves oscillate at a reduced rate. From the clock's own perspective, nothing seems unusual. Every part is slowing together, so the clock appears perfectly normal. Only when it is compared with another clock following a different journey does the difference become visible. This is one of relativity's deepest insights. Time is not something that exists independently of the universe. Time is woven into the processes that occur within it. A tale of two explorers. Let's imagine two friends, Maya and Elias. They graduate from university on the same day, both 25 years old. Maya chooses to remain on Earth, pursuing a career in astronomy. Elias joins the crew of humanity's fastest research spacecraft, which will spend years exploring a distant star system before returning home. The spacecraft travels at an extraordinary fraction of the speed of light. Inside, life feels normal. The crew eat breakfast, conduct experiments, celebrate birthdays, and gaze through observation windows at stars rushing past. Their watches tick normally. Their hearts beat steadily. Plants grow in the greenhouse. Nothing feels unusual. Back on Earth, Maya continues her own life. She builds telescopes, mentors students, and eventually watches her own children grow up. Years later, the spacecraft returns. The reunion is joyful, but surprising. Although both friends have experienced time naturally along their own journeys, Maya has aged more than Elias. Neither clock malfunctioned. Neither person experienced strange sensations. Instead, each followed a different path through space and time, and those paths contained different amounts of elapsed time. To our everyday intuition, this feels impossible. To the universe, it is simply geometry. Moving through space, moving through time. Imagine you have a fixed travel budget for a holiday. The more money you spend on flights, the less remains for hotels and activities. Every choice involves a trade-off. Some physicists like to think about motion in a similar way. Everything in the universe moves through space-time. When an object is nearly at rest relative to you, most of its journey is carried through time. Your life unfolds second by second in a familiar rhythm. As speed through space increases, the balance shifts. More of the journey is devoted to motion through space, and less remains for the passage of time. This isn't because time is being stolen or lost. It's because space and time are deeply connected, like two dimensions of a single fabric rather than separate entities. Although this picture is simplified, it helps us build intuition before introducing the mathematics that physicists use to describe spacetime precisely. Evidence beyond imagination. Whenever an idea seems to challenge common sense, scientists ask an important question. Can we measure it? The answer, in the case of time dilation, is yes. Highly accurate atomic clocks have been flown aboard aircraft and compared with identical clocks left on the ground. Tiny differences appeared exactly as predicted by relativity. Even more impressively, unstable particles created high in Earth's atmosphere survive longer when traveling at enormous speeds. According to classical physics, many should decay long before reaching the surface. Yet large numbers do reach detectors on Earth. From our perspective, their internal clocks are running more slowly during their rapid journey. Nature has performed the experiment countless times. Every result points toward the same conclusion. Time is not fixed. It is dynamic, responsive, and intertwined with motion itself. Rethinking the everyday. It's tempting to think these effects belong only to astronauts and particle physicists. In reality, they are present everywhere. When you walk across a room, your clock changes by an unimaginably tiny amount compared with someone standing still. The effect is so small that no ordinary instrument could ever notice it. Relativity doesn't suddenly switch on at high speeds. It is always present. High speeds simply magnify what has been there all along. In much the same way, the stars remain visible during the day even though sunlight hides them from our eyes. Their presence never disappears, our ability to notice them changes. The same is true for the stretching of time. Chapter 3, When Time Begins to Stretch. Section 2, A Clock Made of Light. Imagine you're aboard a research spacecraft on a journey far from Earth. Inside one of the laboratories is the simplest clock ever conceived. It has no gears, no springs, no batteries, and no digital display. Instead, it consists of two perfectly aligned mirrors facing each other. A single pulse of light bounces endlessly between them. Every time the light reaches the upper mirror and returns to the lower one, the clock records one tick. It sounds almost too simple to be useful, yet this imaginary device reveals one of the deepest truths about reality. While you're sitting inside the spacecraft, the light travels straight up and straight down. Each journey covers exactly the same distance, so every tick takes exactly the same amount of time. To you, nothing unusual is happening. Now imagine a scientist watching your spacecraft pass by from a distant observation station. From their point of view, your spacecraft is moving sideways as the light bounces between the mirrors. The light no longer appears to travel straight up and down. Instead, it traces a zigzag path through space, traveling diagonally as the spacecraft moves. Because diagonal paths are longer than vertical ones, the observer sees the light traveling a greater distance between each tick. Yet one rule remains unchanged. Light always travels at the same speed. If the speed stays the same while the distance becomes longer, only one possibility remains. Each tick must take more time. To the outside observer, your clock is running more slowly. Neither observer has a faulty clock. Each description is correct from its own point of view. This simple thought experiment doesn't rely on unusual materials or mysterious forces. It follows naturally from two ideas we've already explored, the constancy of the speed of light and the fact that motion is always measured relative to an observer. Changing perspective. One of the most challenging aspects of relativity is learning to let go of the idea that there is a single, universal viewpoint. Imagine watching a football match from different seats around a stadium. Someone behind one goal sees the play differently from someone sitting on the halfway line. Neither spectator is mistaken. Each has access to different information because of where they're located. Physics works in a similar way. Observers moving differently through the universe do not always agree on measurements of time and distance, yet the underlying laws of nature remain consistent. This doesn't mean reality is subjective. It means reality is richer than our everyday intuition suggests. Instead of asking, which observer is correct, relativity asks, what do all observers agree on? That question leads to a deeper understanding of the universe. When precision becomes essential. Most of the time, the differences predicted by relativity are unimaginably small. If two friends spend an afternoon cycling at different speeds, the difference in their elapsed time is far too tiny for them to notice. But science often advances by measuring the almost immeasurable. Modern atomic clocks are so accurate that they lose or gain only tiny fractions of a second over incredibly long periods. Instruments like these allow researchers to detect effects that would once have seemed impossible to observe. The lesson is an important one. Nature does not become different simply because the effects are difficult to measure. Sometimes the universe whispers rather than shouts. Progress in science often comes from building instruments sensitive enough to hear those whispers. A new way to think about time. Perhaps the most surprising consequence of relativity is that time is no longer a universal backdrop against which events unfold. Instead, it becomes part of the story itself. Every journey through the universe is accompanied by its own history of elapsed time. Most of the time, those histories remain so similar that we happily share calendars, clocks and schedules without noticing any difference. But when speeds become extraordinary, or, as we'll discover later, when gravity becomes intense, those histories begin to diverge. The universe is not breaking its own rules. It is revealing rules that were always there, waiting to be discovered. Part 1: Foundations of Relativity. Chapter 3: When Time Begins to Stretch. Section 3: The Journey of the Fast Traveler. One of the most fascinating ideas in modern physics is that two people can experience different amounts of time while both are living perfectly normal lives. This sounds strange because our everyday world trains us to believe that time is universal. We arrange meetings, set alarms, celebrate birthdays, and build our entire society around the assumption that everyone shares the same flow of time. And for ordinary situations, that assumption works beautifully. But the universe is not built only for ordinary situations. The universe also contains exploding stars, collapsing galaxies, particles moving almost at the speed of light, and regions where gravity becomes so powerful that even light struggles to escape. To understand nature at these extremes, we must be willing to move beyond everyday intuition. The traveler and the homebound observer. Imagine two siblings, Ava and Leo. They are the same age and grow up together on Earth. When they are 30 years old, Leo joins a deep space exploration mission. His spacecraft is designed to travel at a speed very close to the limit allowed by nature. Ava remains on Earth. Leo's mission lasts what feels like 5 years to him. During that time, he experiences normal life aboard the spacecraft. He eats meals, conducts experiments, sleeps, exercises, and watches the stars drift past his window. When he returns home, he expects to find Ava 5 years older. Instead, he discovers something surprising. Much more time has passed on Earth. Ava has aged significantly more than Leo. At first this sounds like a contradiction. How can one person experience less time than another? The answer is that time is not separate from motion. Their journeys through the universe were different, so their experiences of time were different. They did not disagree about what happened. They simply followed different paths. The meaning of a personal timeline. Every object in the universe follows a path through space and time. Physicists call this path a world line. A world line is not a physical road or a glowing trail behind us. It is a way of describing the complete history of an object, where it was, when it was there, and how it moved through the universe. Your world line began when you came into existence. Every place you have visited, every moment you have experienced, and every movement you have made is part of that journey. A person sitting quietly in a chair has a different world line from an astronaut traveling through space. A mountain has a different world line from a bird flying around it. A planet has a different world line from a comet passing through the solar system. Everything that exists is constantly traveling through space-time. We are all explorers, even when we are standing still. Why time slows rather than speeding up? A natural question arises. If someone is moving very quickly through space, why should their time slow down? Why doesn't it speed up instead? The answer comes from the universe maintaining a deep consistency. The speed of light must remain the same for everyone. Imagine a universal rule that says every observer must measure light traveling at the same speed. If one observer is moving quickly compared with another, something has to adjust to preserve that rule. Nature has two options. Change the measured speed of light, or change measurements of space and time. Experiments show that the speed of light remains constant. Therefore, space and time must adapt. This is one of the central ideas of relativity. The universe does not bend the speed limit. It bends our assumptions about space and time. The aging of the universe's fastest travelers. The effects of time dilation are not just theoretical. Nature provides examples constantly. High-energy particles created in Earth's upper atmosphere often travel at speeds extremely close to light. Many of these particles are unstable and should disappear before reaching the ground. Yet detectors on Earth's surface observe them arriving in large numbers. From Earth's perspective, something unusual has happened. Their internal clocks have effectively slowed because of their extreme speed. From the particle's own perspective, everything feels normal. This difference between perspectives is not a mistake. It is exactly what relativity predicts. The universe allows different observers to experience different amounts of time while still maintaining agreement about the fundamental laws of physics. A new understanding of age. The idea that time can pass differently for different people changes the way we think about aging. Age is not simply a number determined by the date on a calendar. It is connected to the journey an object takes through space-time. Two people born at the same moment can, under extraordinary circumstances, experience different amounts of elapsed time. This does not mean one person is somehow outside reality. Both are experiencing reality fully. Their clocks are simply measuring different journeys. A mountain climber, a deep-sea diver, and an astronaut all experience the passage of time slightly differently because they occupy different environments and move through the universe in different ways. The differences in everyday life are incredibly small, but the principle remains. There is no single cosmic stopwatch hanging above the universe. The practical importance of relativity. It may seem that these ideas belong only to distant spacecraft and science fiction stories. However, understanding time accurately is essential for modern technology. Satellite systems, scientific instruments, and navigation networks depend on clocks that remain synchronized to extraordinary precision. Without accounting for relativistic effects, modern navigation would slowly become inaccurate. The technology around us is quietly confirming one of humanity's greatest discoveries. Every time a navigation system guides a driver to a destination, it is relying on a universe where time is flexible. The human side of relativity. Beyond the mathematics, relativity offers a profound philosophical lesson. Human beings naturally assume that our everyday experience represents the whole universe. For thousands of years, people looked upward and believed the heavens must operate according to the same simple rules they experienced on Earth. But the universe repeatedly surprises us. The Earth is not the center of everything. The Sun is not unique among stars. The Milky Way is only one galaxy among billions. And time itself is not the unchanging river we once imagined. Relativity reminds us that reality is far greater than human intuition. The universe does not have to match our expectations. Our understanding must grow to match the universe. Chapter 4: Space in Motion. Section 1: The Changing Shape of Distance. When we think about distance, we usually imagine something fixed. A road between two towns has a certain length. A football field has a certain size. The distance between Earth and the Moon can be measured and written down. It feels as though distance is simply a property of the world, waiting to be discovered with a ruler. For everyday life, this idea works perfectly. If you measure the length of your garden fence today and again tomorrow, you expect the same result. If your neighbor measures it, you expect them to get the same answer. But once we enter the strange world of extreme speeds, our comfortable ideas begin to change. Just as time can stretch, space can also behave differently depending on motion. The universe does not contain a single master ruler that everyone carries. Instead, measurements of distance depend on the journey of the observer. The problem of measuring a moving object. Imagine a spacecraft traveling past Earth at a speed close to that of light. Inside the spacecraft, the passengers measure their vehicle normally. They check the length of the corridors, measure the distance between rooms, and maintain the ship according to their own instruments. To them, everything appears ordinary. Now imagine scientists on Earth watching the spacecraft race past. They also want to measure the length of the spacecraft. But they discover something surprising. The spacecraft appears shorter in the direction it is traveling. This effect is known as length contraction. It does not mean the spacecraft has been physically crushed. The passengers inside do not feel squeezed. Their equipment does not break. Their bodies do not become thinner. Instead, the measurement of length depends on the observer's motion. This is one of the most difficult ideas in relativity because our everyday experience tells us that objects simply have a size. A chair is a certain length. A building has a certain height. A spacecraft has a certain design. But relativity reveals that measurements are not completely separate from the observer making them. A universal measuring tape does not exist. To understand why distance can change, imagine two people trying to measure a moving train. One person stands beside the railway track. The other person sits inside the train. The person outside sees the entire train pass by and can measure its length by recording where the front and back are at the same moment. The person inside measures the train differently because they are moving with it. The challenge comes from the idea of at the same moment. In everyday life, we rarely question what simultaneous events mean. If lightning strikes two trees at the same time, we assume everyone agrees about that. But relativity shows that agreement about simultaneity is not guaranteed. Two observers moving differently can disagree about whether events happened at exactly the same time. And if people disagree about now, their measurements of distance can also differ. Space and time are connected. Changing one affects the other. The importance of synchronized clocks. To measure distance accurately, we often need clocks. Consider measuring the length of a racing track. You could place one person at the starting line and another at the finish line. When the runner passes each point, the observers record the times. But there is a hidden problem. How do you know the two clocks are perfectly synchronized? If one clock is slightly ahead of the other, your measurement may be incorrect. This seems like a small technical issue, but it reveals something profound. Measuring space requires an understanding of time. And measuring time requires an understanding of space. They are not completely separate ideas. They are connected parts of a larger structure. This was one of the great conceptual breakthroughs of modern physics. Space and time become one. Before modern physics, scientists generally treated space and time as two separate things. Space was the arena where objects existed. Time was the universal clock that measured events. But the discoveries of relativity revealed that this separation was incomplete. Space and time are linked together into something called spacetime. Think of space and time as two threads woven together into a single fabric. Pull one thread, and the other responds. Stretch one part, and the pattern changes. This does not mean spacetime is a physical cloth floating somewhere in the universe. It is a mathematical description of the relationships between events, distances, motion, and time. But the fabric analogy helps us imagine something that is otherwise difficult to picture. The universe is not made of objects moving through a fixed stage. The stage itself is part of the story. Why we don't see space changing around us? At this point, you might wonder, if space can change, why don't I notice it? The answer is the same reason we don't notice time dilation in everyday life. The effects are extremely small at ordinary speeds. A passenger train, an aircraft, or even the fastest spacecraft humans have built so far moves incredibly slowly compared with light. The universe only reveals its deeper behavior when motion becomes extreme. Imagine looking at a large photograph. From a distance, it appears to contain a smooth image. Move closer with a magnifying glass, and suddenly you see tiny details that were always there. Relativity works in a similar way. The unusual behavior of space and time has always existed. We simply needed better instruments and deeper understanding to reveal it. The universe does not prefer one observer. One of the most important lessons of relativity is that no observer has a special position in the universe. Before modern physics, people often imagined that there might be a correct viewpoint from which reality could be measured. But relativity removes that privilege. A person standing on Earth is not observing the universe from a more truthful position than an astronaut traveling through space. A scientist on a planet orbiting another star is not seeing a distorted version of reality. Each observer has their own perspective, and the laws of physics must work equally well for all of them. This idea is both scientific and philosophical. It teaches us that the universe does not revolve around our particular viewpoint. We are participants in reality, not outside observers looking at it from a perfect location. The faster we travel, the stranger reality becomes. As speed increases, the familiar world begins to transform. Clocks disagree. Distances change. Measurements depend on motion. Yet underneath these strange effects is something beautiful. The universe is not chaotic. It is incredibly consistent. The strange behavior of relativity is not a collection of exceptions or tricks. It comes from a simple principle. The laws of nature must remain the same for everyone. The universe adjusts space and time to preserve that harmony. What first appears confusing is actually evidence of a deeper order. A new picture of reality. By now, our old picture of the universe has changed dramatically. We began with the idea that space was a fixed container and time was a universal clock. Now we have discovered something much more flexible. Space can change depending on motion. Time can change depending on motion. Neither exists independently from the other. Together they form the foundation of the universe we experience. This new understanding prepares us for one of the most famous relationships in all of science. If space and time are connected, and if motion changes how we experience them, then energy and matter must also be connected in a deeper way. That connection leads us to one of physics' most famous ideas. E=mc². But the meaning behind that equation is far richer than a simple formula. It reveals that matter is a form of stored energy, and that the objects around us contain an enormous hidden potential. Chapter 5: Energy, Mass, and the Hidden Unity of Nature. Section 1: The Secret Inside Matter. Look around you. The chair you are sitting on, the device you are reading this on, the air around you, the earth beneath your feet, all of these things appear solid and separate. A table is a table. A stone is a stone. A human body is a human body. For most of history, people thought of matter as the basic substance of the universe. Matter was simply stuff, the material things that existed in the world. Energy was considered something different. Energy was movement, heat, light, or the ability to cause change. A piece of wood had mass. A fire had energy. A stone had weight. A flame had warmth. They seemed like completely different aspects of nature. One of the great discoveries of modern physics was that this separation was an illusion. Matter and energy are not strangers. They are different expressions of the same underlying reality. The famous equation. Few scientific equations are as recognizable as E=mc². Many people have seen this equation printed on posters, written in textbooks, or mentioned in films. But its true meaning is often misunderstood. It does not simply mean that energy and mass are related. It reveals something much deeper. Mass is a concentrated form of energy. The E represents energy. The m represents mass. The c represents the speed of light. The small number beside the speed of light, the squared part, makes the relationship extraordinarily powerful. The speed of light is already an enormous number. When multiplied by itself, it becomes an almost unimaginable quantity. This means that even a tiny amount of matter contains a tremendous amount of potential energy. A small piece of material may appear ordinary, but hidden within its structure is an enormous amount of stored energy. Why matter feels so permanent? If matter contains so much energy, why don't everyday objects suddenly release it? Why doesn't a coffee cup explode with the energy hidden inside it? The answer is that matter is remarkably stable. The energy contained within atoms is locked away by the structures that hold them together. Think of a mountain lake. A huge amount of energy exists in the water because of its position high above the valley below. But the water remains still because the conditions are stable. Release the water through a channel, and that stored energy can become motion. Matter works in a similar way. The energy exists, but special conditions are required to unlock it. Nature has powerful barriers that keep ordinary objects stable. This stability is one reason life can exist. The atoms that make up our bodies do not constantly transform into pure energy. They remain organized, allowing complex structures like planets, oceans, forests, and living creatures to exist. The power inside the stars. One of the most beautiful demonstrations of mass becoming energy happens every second inside stars. Our sun appears to be a giant glowing ball of fire, but it is not burning like wood in a fireplace. Instead, it is powered by nuclear reactions deep within its core. The Sun contains enormous amounts of hydrogen. Under extreme pressure and temperature, hydrogen atoms combine to form heavier elements. During this process, a tiny amount of mass disappears. It does not vanish. It is transformed into energy. That energy travels outward through the Sun, eventually reaching Earth as sunlight. The warmth on your skin, the light allowing plants to grow, and the energy that supports almost every ecosystem on Earth began as a transformation of matter inside a star. Every sunrise is a reminder that matter and energy are connected. A universe powered by transformation. Nature is constantly transforming one form of energy into another. A waterfall converts gravitational energy into movement. A battery converts stored chemical energy into electricity. Plants convert sunlight into chemical energy through photosynthesis. Muscles convert chemical energy from food into movement. The universe is not a collection of separate objects that never interact. It is a continuous exchange of energy. Relativity added a profound insight. Matter itself belongs in this same story. The boundary between thing and energy is not as clear as we once believed. The universe is more like a flowing process than a collection of fixed objects. Why the equation changed the world? The relationship between mass and energy transformed science. It helped explain how stars could shine for billions of years. It changed the way physicists understood the structure of atoms. It opened the door to technologies that would have seemed impossible in earlier centuries. However, like many scientific discoveries, the equation also revealed humanity's responsibility. Understanding nature gives us power, but power requires wisdom. The same knowledge that helps us understand stars can also be used in destructive ways. Science itself is neither good nor bad. It is a tool. The choices made by people determine how that tool affects the world. Energy and the story of the universe. The connection between mass and energy also changes how we think about the history of the cosmos. The universe began in an extremely energetic state. Over time, that energy transformed into particles, atoms, stars, planets, and eventually living beings capable of asking questions about their own existence. In a sense, everything around us is part of a long cosmic transformation. The atoms in your body were created inside ancient stars. The energy that drives your thoughts and movements ultimately comes from processes that began billions of years ago. Relativity reveals a universe where everything is connected through a continuous chain of transformation. The hidden simplicity beneath complexity. One of the surprising patterns in physics is that the deepest truths are often expressed through simple ideas. Gravity can be described by the shape of space-time. Motion can be understood through relationships between observers. Mass and energy can be connected through a short equation. But simplicity does not mean the universe is simple. A single musical note can be simple, yet an entire symphony can be extraordinarily complex. A single equation can contain an entire world of consequences. The beauty of physics is discovering the simple principles that create the incredible variety we observe. Chapter 6: Rethinking Gravity. Section 1: The mystery that held the universe together. For thousands of years, human beings looked at the night sky and wondered about the invisible forces controlling the heavens. The moon followed a predictable path around Earth. The planets moved through the darkness in regular patterns. The sun appeared to hold the entire solar system together. But one question remained deeply mysterious. How does gravity actually work? We can observe what gravity does. We can measure its effects. We can calculate the movement of planets and falling objects with extraordinary accuracy. But what is gravity itself? Where does it come from? How does the sun influence Earth across the enormous emptiness of space? These questions reveal one of the greatest transformations in scientific thinking. Before modern physics, gravity was understood as a force. Later, scientists discovered something much more surprising. Gravity is not simply something that happens inside space. Gravity is connected to the very structure of space itself. The genius of Newton's universe. Before exploring the new picture of gravity, we must appreciate the incredible achievement of Isaac Newton. Newton's ideas changed science forever. He discovered that the same laws governing objects on Earth also applied to objects in the heavens. A falling apple and the orbit of the moon were not separate mysteries. They were connected by the same force. Gravity. Newton imagined gravity as an invisible attraction between masses. Every object with mass attracts every other object. The Earth pulls on the moon. The moon pulls on Earth. The sun pulls on planets. Even two people standing near each other exert a tiny gravitational attraction. The reason we do not notice this is that the force between ordinary objects is extremely weak compared with the gravity of massive bodies like planets and stars. Newton's mathematical description was incredibly successful. It allowed scientists to predict eclipses. It explained planetary motion. It guided spacecraft to distant worlds. For more than 2 centuries, Newton's framework was the foundation of physics. But even great theories can leave unanswered questions. The problem of instant influence. Imagine the sun suddenly disappeared. According to Newton's description of gravity, Earth would eventually stop following its orbit and begin moving through space in a straight line. But there is a problem. How would Earth know? The sun is almost 150 million kilometers away. If gravity is a force reaching across empty space, how does that information travel? Does the effect happen instantly? For a long time, scientists accepted this idea because Newton's equations worked so well. But it created an uncomfortable possibility. Gravity appeared to act faster than anything else in nature. If the sun changed, should Earth's orbit adjust immediately? Or should there be some delay? This question became even more important after the discovery that nothing could travel faster than light. A conflict appeared. If light had a speed limit, perhaps gravity should have one too. Nature does not usually contain isolated rules that contradict each other. Scientists began searching for a deeper explanation. Einstein's different question. The breakthrough came when Albert Einstein stopped asking, "What force causes gravity?" and began asking, "What if gravity is not a force in the traditional sense at all?" This was a radical change in perspective. Sometimes the biggest discoveries come not from finding a better answer to an old question, but from asking a completely different question. Imagine watching a person walk across a curved landscape. From one viewpoint, their path might seem strange. They appear to turn left and right for no obvious reason. But then you discover the person is simply following the natural shape of the ground. The path was not caused by an invisible force pulling them around. The environment itself determined the journey. Einstein proposed something similar for gravity. Perhaps objects were not being pulled through space by a mysterious force. Perhaps matter was changing the shape of space itself. The fabric of space-time. Earlier, we explored the idea that space and time are connected into a single structure called spacetime. General relativity takes this idea further. Spacetime is not passive. It can bend, stretch, and change. Mass and energy influence its shape. A simple analogy is a stretched fabric. Imagine placing a heavy ball onto a flexible sheet. The sheet bends around the object. Now roll a smaller ball nearby. Instead of traveling in a perfectly straight line, the smaller ball follows the curved surface created by the larger object. The smaller ball is not being pulled by an invisible hand. It is simply following the shape of the surface. This is not a perfect representation of gravity. The universe is not literally made of fabric, but it helps us imagine the basic idea. Mass changes the geometry of space-time. Objects move through that altered geometry. What we call gravity is the result. Falling is more natural than standing still. One of the most surprising ideas in Einstein's theory is that falling objects are actually following their natural paths. Think about an astronaut floating inside an orbiting spacecraft. They appear weightless. But gravity has not disappeared. The spacecraft is still being pulled toward Earth. So why do the astronauts float? Because they are falling. The spacecraft and everything inside it are continuously falling around Earth rather than falling directly toward it. They are moving sideways fast enough that they keep missing the planet. An orbit is essentially a continuous fall. This changes our understanding of gravity. The sensation of weight is not simply caused by gravity itself. It is caused by resistance to free movement. When you stand on the ground, Earth is preventing you from following your natural path through space-time. The floor pushes upward against your feet. That pressure is what you experience as weight. In a sense, the ground is constantly stopping you from falling. Gravity changes time too. One of the most remarkable predictions of general relativity is that gravity affects time. We already discovered that motion can change the passage of time. But gravity introduces another effect. A clock closer to a massive object ticks slightly slower than a clock farther away. This means that time flows differently depending on where you are. Near Earth, the difference is tiny. Near extremely massive objects, the effect becomes enormous. Imagine two identical clocks. One remains on a mountain. The other sits deep underground. The underground clock experiences slightly stronger gravity and ticks slightly more slowly. The difference is incredibly small, but modern technology can measure it. Again, relativity is not just a strange idea about the universe. It is a description of reality that engineers and scientists must consider. A new vision of the cosmos. General relativity changed the meaning of gravity. Instead of viewing the universe as a collection of objects connected by invisible forces, we now see a dynamic relationship between matter, energy, and the structure of space-time. The universe is not an empty stage. The stage itself moves and changes. Stars shape space. Galaxies influence their surroundings. Planets follow the paths created by the geometry around them. Gravity is not a mysterious pull reaching across the darkness. It is the universe revealing its shape. Part 2. Gravity Reimagined. Chapter 7. The Shape of Space-Time. Section 1. A Universe That Can Bend. For most of human history, people imagined space as an empty container. It was the great stage of existence, a silent, motionless background where stars, planets, and living creatures moved around. If you removed everything from a room, the room would still exist. If you removed every star from the universe, people assumed space would remain unchanged. Modern physics revealed a much more surprising picture. Space is not merely where things happen. Space is part of what is happening. The universe is not sitting inside space. The universe is made with space. And space itself can change. The difference between location and geometry. When we talk about space, we often think only about location. Where is something? How far away is it? What direction must we travel to reach it? But physicists also ask a deeper question. What are the rules of space itself? This is the study of geometry. Geometry describes relationships between objects, distances, angles, shapes, and paths. On a flat sheet of paper, geometry behaves in a familiar way. A straight line is the shortest distance between 2 points. Parallel lines remain separate. The angles inside a triangle always add up to 180 degrees. These rules seem obvious because we experience them every day. But what happens when space itself is curved? The rules begin to change. Living on a curved world. Imagine a group of explorers who live their entire lives on the surface of a giant sphere. They have no knowledge of the world beyond their surface. To them, their environment appears flat. They build houses. They draw maps. They measure distances. They develop their own geometry. If they draw a triangle on their world, they expect the familiar rule about angles adding up to 180 degrees. But they discover something strange. Their triangles do not behave as expected. The angles add up to more than 180 degrees. At first, they may believe their measurements are wrong. But eventually they discover the truth. Their world itself is curved. The unusual geometry was not a mistake. It was a clue about the nature of their environment. In a similar way, scientists discovered that the geometry of our universe is not necessarily the simple, flat structure people once assumed. The invisible influence of shape. One of the hardest things about curved spacetime is that we cannot directly see it. We cannot look through a telescope and observe space bending like a sheet. Instead, we observe what happens to objects moving through it. A planet orbiting a star. Light traveling near a massive object. A spacecraft following a carefully calculated path. The movement reveals the shape. Think about walking through a forest at night. You cannot see the wind directly, but you can see leaves moving and branches swaying. The movement reveals something invisible. Gravity works in a similar way. The paths of objects reveal the structure of spacetime. Why planets orbit instead of flying away? A common question is, if gravity is not a pulling force, why don't planets simply fly away? The answer lies in the relationship between motion and geometry. A planet is moving through space while also following the curved structure created by the Sun's mass. The Sun changes the shape of the surrounding spacetime. The planet follows the natural path available within that geometry. This path creates what we call an orbit. From our everyday viewpoint, it looks like the Sun is pulling the planet around. From the perspective of general relativity, the planet is following the shape of the universe around it. The difference is subtle but profound. Gravity is no longer something added to space. Gravity is the behavior of space itself. Light follows the shape of space. One of the most astonishing consequences of curved spacetime is that even light can be affected. For a long time, scientists thought gravity could only influence objects with mass. A rock could fall. A planet could orbit. But light? Light had no mass, so perhaps gravity could not affect it. General relativity changed that idea. Light travels through spacetime. If spacetime is curved, light follows that curvature. This means a beam of light passing near a massive object can bend. Not because gravity grabs the light like an invisible hand, but because the path through which the light travels has changed. Imagine drawing a straight line on a warped sheet of paper. The line may appear curved from another perspective, even though it is following the straightest possible path on the surface. Light behaves in a similar way. The eclipse that changed science. One of the most famous tests of general relativity involved a total solar eclipse. During an eclipse, the moon blocks the bright surface of the sun, allowing scientists to observe stars that appear close to the sun's position in the sky. According to older ideas, starlight should travel in straight lines unaffected by the sun. According to Einstein's theory, the sun's mass should curve the surrounding spacetime, causing the apparent positions of those stars to shift slightly. When observations were made, the results matched Einstein's prediction. This was a major moment in science. A new theory had successfully predicted an effect that had never been observed before. The shape of spacetime had revealed itself through the movement of light. Spacetime is dynamic. Perhaps the most important idea of general relativity is that the universe is not static. Spacetime is not a rigid framework. It can change. Mass and energy influence its structure. Objects move within it. The universe is a constantly evolving system. This means that every galaxy, every star, and every planet participates in shaping the cosmic environment around it. The Earth does not simply exist inside the universe. Earth contributes, in its own small way, to the structure of the universe. Every object with energy affects space-time. A person. A mountain. A planet. A star. A galaxy. Everything leaves its mark. The beauty of a geometric universe. There is something deeply elegant about this idea. The universe does not require countless separate rules explaining every movement. Instead, a single principle connects everything. Matter and energy shape spacetime, and spacetime guides the movement of matter and energy. The relationship works both ways. The contents of the universe influence the structure of reality. The structure of reality influences the behavior of the contents. It is a cosmic conversation between matter and the space around it. Beyond the human scale. The bending of spacetime may sound like an abstract idea, but it affects the entire universe. It determines how galaxies move, It controls the lives of stars. It influences the paths of light crossing billions of years. It shapes the evolution of the cosmos itself. Every image we receive from distant galaxies has traveled through a universe shaped by gravity. Every observation of the heavens carries the imprint of curved space-time. The universe is not simply showing us objects. It is showing us the geometry that connects them. Chapter 8. Falling through curved space. For thousands of years, humanity looked at falling objects and saw a force pulling them downward. A stone dropped from a hand falls to the ground. The moon circles Earth. The planets follow paths around the sun. The natural conclusion seemed obvious: something must be pulling. But nature often hides its simplest truths behind appearances. Gravity may not be a force that reaches across space and grabs objects. It may be something deeper, a consequence of the shape of the universe itself. To understand this idea, we must change the way we imagine falling. The invisible landscape. Imagine placing a heavy ball on a stretched sheet of fabric. The fabric bends beneath the weight, creating a dip. If a smaller ball rolls nearby, it curves toward the larger one. To someone watching only the smaller ball, it appears as if the larger ball is pulling it. But the smaller ball is not being attracted by an invisible hand. It is simply following the shape of the surface it is moving through. Space itself behaves in a similar way, except that fabric is not something outside the universe. It is the universe. Mass and energy change the structure of space and time around them. Objects then move through that altered structure, following the natural paths available to them. What we call gravity is the result. The straightest possible path. One of the strangest ideas in nature is that objects falling toward Earth are actually moving in the straightest way possible. This sounds impossible. If a person jumps from a height, they accelerate downward. Surely they are not traveling straight? The problem is our everyday meaning of straight. On a flat surface, a straight line means moving without turning. But on a curved surface, the idea changes. Consider traveling across Earth. If you follow the shortest route between two distant cities, you are not moving in a perfectly straight line on a flat map. You are following a curved path because Earth itself is curved. The path is curved only because the space you move through is curved. The same principle applies to the universe. An object in motion follows the natural path through curved space-time. That path is called a geodesic. A planet orbiting a star is not being dragged around by a mysterious force. It is constantly moving along the natural route created by the shape of space-time around the star. A falling object is not being pulled downward. It is following the shape of the universe. Why we feel gravity? If gravity is simply the result of moving through curved space-time, why do we feel it? Why do we feel our feet pressed against the ground? The answer is surprising. When you are standing still on Earth, you are not actually following the natural path of motion. The natural path would be to continue falling toward Earth's center. The ground prevents this. The surface of the planet pushes upward against your body, stopping you from following the path space-time has created for you. The sensation we call gravity is therefore not caused by falling. It is caused by being prevented from falling. An astronaut floating in space feels weightless because they are freely following their natural path. They are not escaping gravity, they are experiencing gravity without resistance. The feeling of weight comes from the interruption of free motion. The universe is not empty. For centuries, space was imagined as a vast emptiness containing objects. Stars existed inside space. Planets moved through space. Space itself was simply the background. But this picture is incomplete. Space is not nothing. The universe has structure. It can stretch, bend, and change. The presence of matter influences this structure, and the structure influences the movement of matter. It is a relationship. Matter tells space how to curve. Space tells matter how to move. Neither exists as a completely separate thing. The universe is not a collection of objects sitting inside a container. The universe is the container and the objects together. Gravity's hidden connection. The deeper we look at gravity, the less it resembles a traditional force. Electricity and magnetism involve fields that spread through space. Gravity also has a field-like influence, but its nature is different. Gravity is connected to the geometry of reality itself. It is not merely something happening inside the universe. It is something happening to the universe. A star does not simply sit in space and create a pull around itself. The star changes the environment around it. The space and time surrounding the star become different from the space and time far away. Near a massive object, time itself changes. Distances change. Paths change. Reality becomes shaped by the presence of energy. The river of space. A useful way to imagine gravity is to think of space as a flowing river. An object floating in a river does not need to be pushed downstream. The movement of the river carries it. A leaf does not decide to travel toward the ocean. It follows the flow. In the same way, planets, moons, and even light travel through the changing currents of space-time. The universe has a structure, and everything within it participates in that structure. We are not separate observers standing outside reality. We are part of the movement. A new understanding of falling. The word falling suggests movement toward something. But perhaps falling is not about being pulled. Perhaps falling is about following. The universe creates pathways through its own geometry, and objects move along those pathways naturally. A planet is not fighting against space to stay in orbit. A photon of light is not choosing to bend when it passes near a massive object. They are simply following the shape of reality. Gravity is not a command given to matter. It is the language spoken by the universe itself. Beyond the force. Understanding gravity in this way changes our relationship with the cosmos. The universe is not built from separate pieces connected by invisible strings. It is a connected system where everything influences the structure around it. Every star shapes the space nearby. Every galaxy changes the landscape of the universe. Every particle participates in a larger cosmic design. Gravity is not merely something that happens between objects. Gravity is a reminder that everything exists within a deeper framework. Space is not the stage. Space is part of the story. And when we learn to see falling not as being pulled, but as moving naturally through the shape of reality, we begin to understand that the universe is far more dynamic than it first appears. The next question becomes even deeper. If space and time can bend, stretch, and change shape, what happens when the entire universe itself begins to evolve? That is where our journey continues. Chapter 9. The universe that can expand. For most of human history, the universe appeared eternal and unchanging. The stars seemed fixed in place. The heavens looked like a permanent structure that had always existed and always would. The idea that the universe itself could grow, stretch, or evolve was almost impossible to imagine. Space was thought of as a silent stage. The stars moved. The planets moved. But the stage itself remained. Modern understanding revealed something far more extraordinary. The stage can move too. The universe is not simply where events happen. The universe is one of the things that happens. The discovery that changed everything. When astronomers began studying distant galaxies, they noticed something unexpected. Almost every galaxy beyond our local neighborhood appeared to be moving away from us. At first, this seemed to suggest that Earth occupied a special position in the universe, with everything racing away from our location. But there was another explanation. The universe itself could be expanding. Imagine drawing dots on the surface of a balloon. The dots represent galaxies. As the balloon inflates, every dot moves away from every other dot. No single dot is the center. The distance between the dots increases because the surface itself is stretching. The galaxies are not necessarily traveling through space like objects moving through an empty room. Space itself is changing between them. The universe is growing. Expansion is not an explosion. One of the most common misunderstandings is imagining the beginning of the universe as an explosion. An explosion happens in a place. Fragments fly outward into surrounding space. But the expansion of the universe is different. There was no empty space waiting outside the universe for it to expand into. Space itself was part of the process. The universe did not expand into something else. It expanded as something else. The difference is subtle but profound. The universe is not an object sitting inside a larger container. There is no external room surrounding reality. The expansion is the changing relationship between everything within reality. The stretching of space. When we say the universe expands, we do not mean that individual objects are becoming larger. Atoms do not expand. People do not expand. Planets do not expand. The forces holding these things together are much stronger than the effects of cosmic expansion. Instead, expansion happens on the largest scales. The space between distant galaxies increases. The universe creates more distance between structures that are not strongly bound together. A galaxy does not need to push itself away from another galaxy. The space between them changes. This is one of the most unusual ideas in physics. Movement can occur without something moving through space. Sometimes space itself moves. The light that carries the past. The expanding universe also changes the way we see distant objects. Light takes time to travel. When we look at the sun, we see it as it was several minutes ago. When we look at distant galaxies, we see them as they existed millions or billions of years in the past. The universe becomes a kind of natural time machine. But expansion adds another layer. As light travels across expanding space, its wavelength stretches. A wave of light leaving a distant galaxy begins its journey with a certain pattern. During its enormous journey, the space carrying that light expands, stretching the wave along with it. The light becomes shifted toward longer wavelengths. This tells us something remarkable. The universe leaves fingerprints on the light passing through it. By studying those fingerprints, we can learn how the universe has changed over time. The universe has a history. An expanding universe means the cosmos has a story. It has a past. It has experienced different stages. The universe we see today is not the same universe that existed billions of years ago. Earlier in cosmic history, everything was closer together. Temperatures were higher. Matter existed in different forms. Stars and galaxies had not yet formed. The universe evolved from a simpler, hotter state into the complex structure we observe today. The cosmos is not a finished painting. It is a painting still being created. Gravity versus expansion. At first, expansion seems to contradict gravity. If gravity pulls things together, why does the universe expand? The answer is that both processes exist at the same time. Gravity shapes local structures. It brings matter together. It creates stars, planets, and galaxies. Expansion operates across the largest distances. The two are not enemies. They work on different scales. A galaxy can remain held together by gravity while the space between galaxy groups continues to expand. A person can stand on Earth while the universe grows around them. The changing universe does not erase the structures within it. It creates the environment in which those structures exist. A universe still becoming. Perhaps the most profound lesson of cosmic expansion is that reality is not fixed. The universe is not a completed object that was created once and left unchanged. It is an evolving system. Space changes. Time changes. Matter changes. The relationships between all things change. The universe has a direction. Not a direction through space, but a direction through transformation. From simplicity came complexity. From energy came matter. From matter came stars. From stars came planets. From planets came life capable of looking back and asking questions about the universe itself. The cosmos has become aware of its own existence through the beings it created. Beyond a static universe. The old picture of a permanent, unchanging universe gave humanity a sense of stability. The new picture gives something deeper. It reveals a universe that is alive with motion. Galaxies are not simply arranged across an eternal landscape. They are participants in a cosmic process. Space itself has a history. The universe has memories written into its structure. Every distant galaxy, every beam of ancient light, and every particle carries information about a reality that is still unfolding. The universe is not a place we are inside. It is a process we are part of. And if the universe can expand, transform, and evolve on the greatest scale imaginable, then the next mystery becomes unavoidable. What is the fate of a universe that is constantly changing? That question leads us deeper into the final chapters of Gravity's hidden story. Chapter 10. The Dark Side of the Cosmos. The universe is filled with things we can see. Stars shine. Galaxies glow. Nebulas paint the darkness with clouds of gas and light. Yet when we study the cosmos carefully, we discover something unexpected. Most of the universe is invisible. The matter we can see, the stars, planets, gas, and everything that makes up our everyday experience, appears to be only a small part of what exists. The universe contains a hidden structure. Something unseen shapes the movements of galaxies, influences the growth of cosmic structures, and determines the future of everything. We call these mysteries dark matter and dark energy. But these names do not describe what they are. They describe what they are not. They are reminders that the universe still holds secrets. Seeing the invisible. Human beings have always relied on light to understand the universe. Our eyes detect only a narrow range of electromagnetic waves, but through technology we have learned to observe the cosmos in many different ways. Radio waves reveal hidden structures. X-rays reveal energetic events. Infrared light shows objects hidden behind dust. Each discovery expanded our view of reality. But sometimes the universe tells us about things without showing them directly. We can know something exists because of its influence. A planet can be discovered by watching a star move slightly because of the planet's gravity. A hidden object can reveal itself through the effects it creates. The universe does not always reveal its contents through appearance. Sometimes it reveals them through behavior. The mystery of galactic motion. When astronomers studied the movement of stars inside galaxies, they found something strange. Stars near the outer edges of galaxies were moving much faster than expected. According to the visible matter alone, these stars should have been moving too quickly to remain attached to their galaxies. The galaxies should have slowly torn themselves apart. But they did not. Something was holding them together. There appeared to be more mass present than could be seen. An invisible source of gravity was shaping the motion of stars. This unseen influence became known as dark matter. The invisible framework. A useful way to imagine dark matter is as a hidden framework supporting the visible universe. The stars and galaxies we observe may be like lights attached to an enormous invisible structure. The structure itself cannot be seen directly, but its presence can be detected through the way visible matter behaves. Dark matter appears to provide the gravitational foundation around which galaxies form. Without it, the universe may not have developed the rich patterns we observe today. The cosmic web of galaxies, the vast network connecting billions of galaxies across space, may owe much of its existence to this hidden component. The universe we see may be only the surface of a much larger reality. The search for dark matter. One of the greatest challenges in modern science is discovering what dark matter actually is. Many possibilities have been considered. Perhaps it consists of particles unlike anything we have discovered. Perhaps it belongs to a hidden part of nature that interacts only weakly with ordinary matter. Perhaps our understanding of gravity itself requires modification. The search continues because the answer would transform our understanding of the universe. Discovering dark matter would not simply add another item to a list of cosmic objects. It would reveal a new layer of reality. The universe begins to accelerate. Dark matter explains how galaxies can remain connected. But another mystery appeared when scientists studied the expansion of the universe itself. For a long time, many expected gravity to slow the expansion down. Gravity attracts. Gravity gathers. Gravity resists separation. But observations revealed something astonishing. The expansion of the universe is speeding up. Something appears to be driving galaxies apart faster over time. This unknown influence became known as dark energy. The energy of empty space. One possibility is that space itself contains a form of energy. What we call empty space may not truly be empty. Even a vacuum may possess a hidden background activity. If space carries energy, then as the universe expands and more space exists, the influence of that energy may become increasingly important. The emptier the universe becomes, the more dominant this hidden effect could become. Reality may contain an energy built into the structure of space itself. The balance of the cosmos. The universe is shaped by competing influences. Gravity pulls matter together. Expansion separates distant structures. Dark matter helps create cosmic structure. Dark energy influences the future expansion of space. Together, these unseen forces determine the story of the cosmos. The visible universe is not the whole universe. It is a small window into a much larger system. We are like creatures living on the surface of an ocean, able to see the waves but unable to see the immense world beneath them. The humbling lesson. The discovery of dark matter and dark energy changed humanity's understanding of its place in the cosmos. For centuries, we believed we were studying a universe made mostly of familiar things. Then we discovered that the familiar things may be the exception. The majority of reality may exist beyond direct observation. This does not mean the universe is unknowable. It means knowledge requires humility. Nature does not reveal itself all at once. Each discovery opens a larger question. Each answer reveals a deeper mystery. The darkness of the universe is not an absence of understanding. It is an invitation to explore. Beyond what we can see. The greatest discoveries in science often begin with a simple realization. Something does not make sense. A planet moves strangely. A star behaves unexpectedly. A galaxy rotates too quickly. These moments of confusion become doors leading to deeper understanding. The invisible universe is not separate from the visible one. It shapes everything we experience. The atoms in our bodies, the stars above us, and the galaxies surrounding us all exist within a reality far larger than our senses can detect. We are not observers standing outside the mystery. We are part of the mystery. And as we continue exploring beyond what can be seen, we approach an even greater question. If the universe is filled with hidden structures and unseen influences, what lies at the deepest foundation of reality itself? That question leads us toward the final frontier. Chapter 11. The Architecture of the Universe. When we look at the night sky, we see countless points of light scattered across darkness. To the human eye, the universe appears almost random. Stars seem separated. Galaxies appear isolated. The vast emptiness between them gives the impression of a cosmos without structure. But beneath this appearance lies an incredible order. The universe is not a collection of disconnected objects. It is a vast architecture. A structure built across unimaginable distances, shaped by gravity, energy, and the mysterious rules that govern existence itself. The cosmic design. Human beings are naturally drawn to patterns. We find shapes in clouds. We recognize familiar forms in stars. We search for order because patterns reveal information. The universe is filled with patterns far greater than anything we encounter on Earth. Galaxies gather into groups. Groups form clusters. Clusters connect into enormous chains and networks stretching across billions of light years. This structure is known as the cosmic web. It resembles a giant network of invisible threads, with galaxies gathering along these cosmic pathways. The universe is not evenly arranged. It has shape. The invisible blueprint. The formation of this cosmic structure began with tiny differences in the early universe. At first, these differences were incredibly small. Some regions contained slightly more matter than others. Some areas were slightly denser. Over enormous periods of time, gravity amplified these differences. Areas with more matter attracted more matter. Small variations became larger structures. Clouds became galaxies. Galaxies became clusters. The universe transformed simple beginnings into extraordinary complexity. The patterns we see today were written into the universe's earliest moments. Gravity as the builder. Gravity is often described as an attractive force, but it is more than that. Gravity is an architect. It shapes the arrangement of matter across the universe. It gathers dust into stars. It organizes stars into galaxies. It brings galaxies into communities. Without gravity, the universe might remain a thin collection of particles spread across empty space. With gravity, complexity becomes possible. The same principle that causes an apple to fall also helps create the largest structures in existence. The smallest moments and the greatest cosmic events are connected by the same underlying rule. The scale of reality. One of the greatest challenges in understanding the universe is accepting the enormous difference between human experience and cosmic reality. Our lives occur on a tiny scale. We measure distances in meters. We experience time in years. The universe operates across billions of light years and billions of years. A galaxy is not merely a large object. It is a city of stars. A cluster of galaxies is not merely a collection. It is a gravitational community. The universe operates at levels far beyond human intuition. Yet the same laws apply everywhere. The physics of a falling object on Earth is connected to the physics of galaxies moving across the cosmos. Reality is unified. The universe as a living system. The word living is usually reserved for organisms. But the universe has qualities that remind us of a living process. It changes. It develops. It creates new forms. It moves from simplicity toward complexity. Stars are born and die. Elements are created inside stars. Those elements become planets. Planets can become homes for life. The universe is not alive in the biological sense. But it behaves like an unfolding system. A process constantly transforming itself. The role of time. The architecture of the universe cannot be separated from time. A photograph of the cosmos only shows one moment in a much longer story. A galaxy is not simply a thing. It is a chapter. A star is not merely an object. It is a process. Everything we see is temporary. The universe is not a collection of permanent structures. It is a continuous transformation. Even the most enormous galaxies will eventually change. Even the universe itself is changing. Time is not simply a background where events occur. Time is part of the architecture. The universe looking back at itself. There is something remarkable about our ability to study cosmic structure. The universe created stars. Stars created the elements necessary for planets. Planets created environments where life could emerge. Life developed intelligence. Intelligence developed curiosity. And now the universe can examine itself. Through human observation, the cosmos has produced a way to become aware of its own existence. We are not separate from the universe studying it from outside. We are one of the universe's own creations exploring its origins. The limits of our understanding. Even with all our discoveries, the architecture we understand may only be part of a much deeper design. We know that space and time are connected. We know gravity is linked to geometry. We know the universe expands. We know invisible influences shape its evolution. But beneath all of this lies a question. Why does the universe have the structure it has? Why these laws? Why these constants? Why does anything exist at all? Science continues by approaching these questions one step at a time. Each discovery reveals more of the architecture. Each mystery points toward deeper layers. Beyond the cosmic blueprint. The universe is not a chaotic accident of unrelated events. It is a connected system where every level influences another. Particles form atoms. Atoms form stars. Stars form galaxies. Galaxies form a cosmic structure. And within that structure, consciousness emerges. The universe has built complexity from simplicity. It has transformed invisible rules into visible wonders. The night sky is not just a collection of lights. It is the visible expression of a hidden architecture. And as we continue our journey beyond relativity, we must now ask an even deeper question. If the universe has an underlying structure, could the laws that govern it themselves be connected into one complete description of reality? That search brings us to the next great idea. Chapter 12. The Dream of a Unified Universe. Throughout history, humanity has searched for connections. We have looked at the world around us and discovered that things once thought separate were actually parts of a greater whole. The lightning in the sky and the electricity flowing through a wire were once considered different phenomena. The movements of planets and the falling of objects on Earth once appeared unrelated. Again and again, nature has revealed that separate pieces can belong to one deeper pattern. The greatest unfinished search in physics follows the same path. It is the search for unity. A single understanding that explains the foundations of reality. The hidden connections of nature. The universe appears to contain many different forces and behaviors. Gravity shapes planets and galaxies. Electromagnetism controls light, chemistry, and the structure of atoms. Other forces operate deep inside the smallest particles. At first glance, these seem like separate parts of nature. Different rules. Different scales. Different languages. But history has shown that nature often hides simplicity beneath complexity. What appears to be many things may be different expressions of something deeper. From separate forces to one understanding. The first great unifications changed humanity's view of reality. Electricity and magnetism were once treated as separate mysteries. Then scientists discovered they were connected. They were not two forces. They were one force with different expressions. Light itself emerged as part of this same connection. A beam of light, a magnetic field, and an electric current became understood as parts of a single electromagnetic reality. This discovery revealed an important lesson. Nature does not need to follow the divisions created by human thinking. The universe does not organize itself according to our categories. The challenge of gravity. Gravity remains one of the greatest mysteries in this search for unity. Our understanding of gravity is incredibly successful on large scales. It explains the movement of planets. It describes the behavior of stars. It predicts how space and time respond to matter and energy. Yet when we explore the smallest scales of nature, gravity becomes difficult to combine with the other fundamental ideas of physics. The universe appears to speak two different languages. One language describes the enormous. The other describes the tiny. The challenge is discovering whether both are chapters of the same story. The two worlds of reality. The very large and the very small seem surprisingly different. On cosmic scales, space and time can stretch, bend, and evolve. Massive objects influence the shape of the universe itself. On microscopic scales, particles behave in ways that challenge everyday experience. They do not always behave like tiny solid objects. They exist according to patterns of probability and possibility. Both descriptions have been tested with extraordinary accuracy. Yet bringing them together remains one of the greatest goals of science. Somewhere beneath both views may exist a deeper foundation. Searching beneath space and time. Perhaps the greatest possibility is that space and time themselves are not the final layer of reality. Perhaps they emerge from something more fundamental. Just as a wave emerges from the movement of water, space-time itself may arise from a deeper structure we have not yet discovered. This idea changes the question. Instead of asking, what happens inside space and time? We begin asking, where do space and time themselves come from? The universe may have layers of reality, with each deeper layer explaining the one above it. The limits of human intuition. The search for unity is difficult because our brains evolved to understand everyday experiences. We understand objects. We understand movement. We understand distance. But the deepest levels of reality may not behave like anything we encounter in ordinary life. A person from centuries ago would have struggled to imagine invisible fields, curved space, or the stretching of time. The discoveries of the future may seem equally strange. The universe does not have to match our intuition. Our understanding must expand to match the universe. Why unity matters. A unified description of reality would not simply be a more convenient scientific formula. It would reveal something profound about existence. It would tell us whether the universe is built from separate ingredients or from a single underlying principle. It would show whether the diversity of nature is fundamental or whether it emerges from deeper simplicity. The colors of a rainbow appear separate, but they come from one source, light. Perhaps the many forms of reality are similar. Perhaps everything we observe emerges from one deeper foundation. The universe as one story. The search for unity is not only a scientific journey. It is a philosophical one. It asks whether everything in existence is connected. The atoms inside our bodies were created in ancient stars. The forces shaping galaxies also influence the smallest particles. The history of the universe is not a collection of separate events. It is one continuous process. From the birth of the cosmos to the thoughts inside a human mind, everything belongs to the same unfolding story. Beyond the search for a theory, the dream of a unified universe is not about reducing the beauty of reality into a simple answer. It is about understanding the hidden relationships beneath that beauty. A musician does not destroy a song by understanding harmony. A painter does not remove wonder by understanding color. Knowledge can deepen mystery rather than eliminate it. The more we learn, the more remarkable existence becomes. The next horizon. We have traveled from the illusion of absolute space and time, through the speed limit of the universe, into the bending of reality itself. We have seen gravity transformed from a pulling force into the shape of space-time. We have discovered that the universe expands, evolves, and contains hidden structures beyond direct observation. Now we stand at the edge of the next question. If the universe is connected by deeper principles, could reality itself have a beginning, a boundary, or a hidden origin? To understand where everything came from, we must look toward the birth of the universe itself. Chapter 13. The beginning without a beginning. Human beings have always asked the same profound question. Where did everything come from? Every object we encounter appears to have an origin. A tree grows from a seed. A building begins with a foundation. A person begins with a moment of creation. So when we look at the universe, it feels natural to ask, what came before it? What caused reality to exist? But the universe challenges our usual way of thinking. Perhaps the beginning of everything was not an event that happened inside time. Perhaps the beginning was the moment when time itself came into existence. The edge of time. Our minds are built around the idea of before and after. Every event seems to require something that came earlier. A river requires a source. A journey requires a starting point. But time itself is different. If time has a beginning, then asking what happened before that beginning may not make sense. It would be like asking, what is north of the North Pole? The question assumes something exists beyond a boundary where the concept no longer applies. The universe may not have begun at a particular location in space. It may have begun with the creation of space itself. The early universe. The young universe was unlike anything we experience today. It was not a collection of stars floating in darkness. There were no galaxies. No planets. No familiar structures. Instead, the universe existed in an extremely hot and dense state. The conditions were so different that our everyday concepts begin to fail. Space and time themselves were part of this evolving reality. As the universe expanded and cooled, new possibilities emerged. Particles formed. Atoms developed. Stars eventually ignited. The complexity we see today grew from a much simpler beginning. The universe became more than it first appeared capable of becoming. Creation without a creator event. When people hear the word beginning, they often imagine a single dramatic moment. A starting gun. A first movement. A sudden arrival. But the origin of the universe may not be understood that way. The birth of reality may be less like a spark appearing in darkness and more like a gradual unfolding of possibilities. The laws of nature, the structure of space, and the flow of time all emerge together. The universe did not enter an already existing stage. The universe created the stage. The mystery of why there is something. Even if we understand how the universe evolved from its earliest moments, a deeper question remains. Why does anything exist at all? Why is there something rather than nothing? Science can describe processes. It can explain how matter behaves. It can trace the development of the cosmos. But the ultimate mystery of existence reaches beyond simple explanations. The fact that there is a universe to study is itself one of the greatest mysteries. Reality exists. And within reality, consciousness has emerged to question its own existence. The fine balance of nature. The universe appears to follow precise patterns. The properties of matter. The behavior of energy. The relationships between forces. Small changes in these foundations could create a universe very different from the one we know. This raises deep questions about the nature of reality. Are the laws of physics the only possibilities? Are there deeper principles that determine them? Is the universe one possibility among many? These questions remain open. The search continues. A universe that creates. One of the most remarkable discoveries of modern thinking is that the universe is not simply a place where things happen. It is a system capable of producing new forms of existence. The early universe produced stars. Stars produced heavier elements. Those elements formed planets. Some planets developed life. Life developed awareness. Awareness developed the ability to study the universe. The cosmos has created beings capable of reflecting on its own origin. In a sense, the universe has become a way for itself to ask questions. The beginning is everywhere. We often imagine the beginning of the universe as a distant moment billions of years ago. But the effects of that beginning surround us constantly. Every atom in our bodies carries a history connected to the early cosmos. Every star contains the story of ancient processes. Every breath we take involves elements created through the life and death of stars. The beginning is not simply behind us. It is present within everything. Beyond the first moment. The search for the origin of the universe teaches us something important. Reality is deeper than our first impressions. A beginning may not be a point on a timeline. A cause may not always come before an event. An empty space may not truly be empty. The universe repeatedly forces us to expand our understanding. The questions become greater as the answers become clearer. And perhaps the greatest lesson is this. The universe is not something that simply appeared. It is something that continues to unfold. Toward the final questions. We have explored the movement of time, the structure of space, the nature of gravity, the hidden components of the cosmos, and the possible origins of reality itself. But one final mystery remains. All of these discoveries describe the universe from the outside. They explain its structure. They explain its behavior. They explain its history. But there is another question. What does it mean for a universe like this to contain observers who can experience it? Where does consciousness fit into the cosmic story? That is the final frontier. Chapter 14. The universe within us. For most of human history, we have looked outward. We have studied the stars, measured the planets, and searched the depths of space for answers about existence. The universe above us has always inspired wonder. But there is another direction we can explore. Inward. The same universe that stretches across billions of light years also exists within the smallest parts of ourselves. The atoms that make our bodies. The energy that powers our cells. The elements that allow life to exist. All are connected to the history of the cosmos. We are not visitors in the universe. We are the universe experiencing itself. The story written in atoms. The human body appears separate from the stars. We walk on Earth. We breathe the atmosphere. We experience life through our senses. Yet the materials that make us were created through ancient cosmic processes. The hydrogen in the universe's earliest moments became the foundation for countless structures. Inside stars, new elements were formed through the pressure and heat of nuclear reactions. When massive stars ended their lives, they scattered these elements into space. Those elements later became planets, oceans, and living things. The carbon in our cells. The oxygen we breathe. The minerals in our bones. All carry a cosmic history. The universe did not simply create a place for life. It created the ingredients for life. From matter to mind. One of the greatest mysteries in existence is consciousness. The universe contains matter. Matter follows physical laws. But somehow, through the complex organization of matter, awareness appears. A collection of atoms can become something capable of thought. A physical system can become capable of questioning its own existence. This transition from simple ingredients to conscious experience remains one of the deepest mysteries we know. How does the universe produce beings that can understand the universe? The question leads us into unexplored territory. The observer and reality. Human beings have always wondered whether the universe exists independently of observation. Does reality exist exactly as it is, whether anyone sees it or not? Or does observation play a deeper role? Modern physics has shown that measurement and observation are more subtle than everyday experience suggests. At the smallest scales, nature does not always behave like the predictable world of everyday objects. Particles can exist in ways that challenge our ordinary ideas about certainty and reality. This does not mean that consciousness creates the universe. Rather, it shows that the relationship between observer and reality is more complex than we once imagined. We are not completely separate from what we study. We are part of the system we are trying to understand. The universe becoming aware. Consider the journey of the cosmos. At the beginning, there were no stars. No planets. No living beings. Only simple conditions and fundamental processes. Over time, complexity emerged. Matter organized itself into structures. Stars created the elements. Planets formed environments. Life developed. Eventually, a small creature on a small planet became capable of looking into space and asking, "What is all of this?" The universe has produced a form of awareness capable of exploring its own origins. This is one of the most extraordinary facts we know. The cosmos has created a way to reflect upon itself. The separation illusion. Humans often feel separate from nature. We imagine ourselves as observers looking at an external universe. But the boundary is not as clear as it appears. The atoms in our bodies were once part of ancient stars. The energy that sustains us comes from the same physical processes that shape the cosmos. The laws governing distant galaxies are the same laws governing the particles within us. The universe is not divided into us and everything else. There is one continuous reality. Knowledge and wonder. Understanding the universe does not remove its mystery. Sometimes people fear that scientific explanations make reality less beautiful. The opposite is true. Knowing that a star is a vast nuclear furnace does not make it less magnificent. Knowing that the elements in our bodies were created in ancient cosmic events does not make life less meaningful. Understanding adds depth. A sunset is not less beautiful because we understand light. A song is not less powerful because we understand sound. Knowledge reveals hidden layers of wonder. Our place in the cosmos. The universe is unimaginably large. Earth is a tiny world orbiting one ordinary star among countless others. Yet within this small corner of reality, something remarkable has happened. The universe has developed a form that can ask questions. It can explore. It can imagine. It can seek understanding. Our importance does not come from being the center of the universe. It comes from being connected to the universe. We are part of a story far older and larger than ourselves. Beyond the human perspective. The journey beyond relativity has shown us that our first impressions of reality are often incomplete. Space is not simply empty distance. Time is not simply a universal clock. Gravity is not merely a pulling force. The universe is not static. Reality is deeper than appearance. And perhaps the greatest discovery is that the observer and the universe are not separate. The universe is not something we merely look at. It is something we belong to. The final horizon. We have reached the final chapter of our journey. We began by questioning our everyday understanding of space and time. We traveled through the speed limit of the universe, the stretching of time, the bending of space, the nature of gravity, the expansion of the cosmos, and the hidden structures that shape reality. Now only one question remains. After everything we have learned, how should we see the universe? Not simply as a collection of objects. Not simply as a machine. But as a connected, evolving reality of which we are an inseparable part. The final chapter explores this new perspective. Chapter 15. Beyond Relativity, a New Vision of Reality. Every great journey begins with a question. Not an answer. A question. For centuries, humanity looked at the universe and accepted the appearance of things. Space seemed like an endless empty container. Time seemed like a single river flowing equally for everyone. Gravity seemed like a mysterious invisible pull. Matter seemed separate from energy. The universe seemed like a collection of objects existing independently from one another. But every discovery revealed something deeper. The universe was not what it first appeared to be. It was more connected, more dynamic, more mysterious, more beautiful. The end of the old picture. The old view of reality imagined the universe as a giant machine. Objects moved through space. Clocks measured time. Forces acted between things. Everything appeared separate and predictable. This picture worked remarkably well for everyday experiences. But when we explored deeper, nature revealed a different story. Space and time were not fixed. They could stretch and change. Energy and matter were not separate. They were connected expressions of the same foundation. Gravity was not simply a force reaching across empty space. It was the response of reality's own structure. The universe was not a machine operating inside a stage. The universe was the stage, the machine, and the process together. A universe of relationships. Perhaps the greatest lesson from modern understanding is that nothing exists completely alone. Everything is defined through relationships. A planet exists through its relationship with its star. A star exists through its relationship with gravity, matter, and time. Matter exists through its relationship with energy. Even space itself exists as part of a larger cosmic structure. Reality is not built from isolated pieces. It is built from connections. The universe is not a collection of things. It is a network of relationships. The deeper meaning of gravity. Gravity began our journey because it seemed simple. An object falls. A planet orbits. A star attracts. But beneath these familiar experiences was a deeper truth. The universe has shape. Mass and energy influence that shape. Everything moves through the structure created by everything else. Gravity teaches us that the universe is not passive. Reality responds. The presence of something changes the environment around it. Every star, every planet, and every particle contributes to the story of the cosmos. A universe still unfolding. One of the most important changes in perspective is understanding that the universe is not finished. It is not a completed object sitting in eternity. It is an unfolding process. Galaxies form. Stars are born. Elements are created. Worlds change. Life emerges. Consciousness appears. The universe continues creating new possibilities. The cosmos is not merely something that happened. It is something that is happening. The limits of knowledge. The more we discover, the more questions appear. This is not a failure. It is a sign that we are moving deeper. Every answer opens another doorway. The universe remains mysterious because reality is richer than any single explanation. Even the greatest theories are not the universe itself. They are maps. Powerful maps. Beautiful maps. But maps of something far greater. The purpose of science is not to remove mystery. It is to understand mystery more clearly. Beyond relativity. The title of this journey does not mean leaving relativity behind. It means moving beyond the first transformation in our understanding. Relativity showed us that space and time are connected. It revealed that reality depends on relationships. It changed our understanding of motion, gravity, and the universe itself. But every great idea becomes the foundation for the next discovery. Beyond relativity lies the ongoing search for deeper connections. A more complete understanding. A greater picture. The journey continues. Humanity's place in the cosmos. We often look at the universe and feel small. The scale of space is overwhelming. Billions of galaxies. Trillions of stars. Distances beyond imagination. But size alone does not determine significance. A single thought can contain a universe of meaning. A single question can change humanity's understanding forever. Our ability to wonder is itself a cosmic achievement. The universe has produced beings capable of asking about its origins. Through us, the universe has gained the ability to look back upon itself. The universe within and without. The journey outward and the journey inward eventually meet. The smallest particles and the largest galaxies are connected through the same underlying reality. The atoms within us were formed through cosmic history. The laws that shape distant galaxies also shape our own existence. We are not separate from the universe we study. We are a part of it. The universe is not merely around us. It is within us. A new way of seeing. Perhaps the greatest transformation is not learning new facts. It is learning a new way to see. To see space as something active. To see time as something flexible. To see gravity as geometry. To see matter as connected to energy. To see ourselves as participants in a cosmic story. The universe becomes less like a collection of objects and more like a living tapestry of relationships. Every thread influences the whole. Every part belongs to the pattern. The journey never ends. We began with simple questions. What is space? What is time? Why do things fall? How does the universe work? Those questions led us deeper than expected. They revealed a reality stranger and more wonderful than imagination alone could create. But the greatest discoveries may still be ahead. There may be deeper layers of reality waiting to be understood. New connections waiting to be discovered. New ways of seeing existence waiting to emerge. The universe remains an open book. And we are both the readers and part of the story being written. Final reflection. Beyond relativity is not a destination. It is a way of thinking. A reminder that reality is deeper than appearances. That certainty can become curiosity. That mystery can become exploration. That every answer can lead to a greater question. The universe is vast. The universe is ancient. The universe is changing. And somehow, within this immense cosmic process, there exists a small part of the universe capable of wondering about it all. That part is us. We are the universe becoming aware of itself. And the journey has only begun. Feel free to like and subscribe if you like these audiobooks.